All right, so I'm going to be talking about the JVM at Google. Who am I? Who am I? Why am I up here? Why am I standing here? I work at Google on Java at Google. That's probably not surprising. What do we have at Google? Do we use Java? Yes, we use Java. We use a lot of Java. We have lots and lots and lots and lots of Java developers. We have lots and lots and lots and lots and lots and lots and lots of Java code. We have a lot of programs written in Java running everywhere. And you know, when you get to that size, you'll notice there are people here from Facebook and people here from GE and Ericsson and all these. And you sort of start to ask, well, what can we do a little differently with the JDK and the JVM? And at least help our users get over some of their more difficult pain points. So we built a JDK team and it deploys. We deploy the JDK, we maintain the JDK, we enhance the JDK. It's used by all sorts of different parts of Google. It's used by Gmail, it's used by Google Plus and Docs and Blogger, and our build system uses it, and AdWords uses it, and all sorts of different people use it. Some people I'm not even allowed to tell you use it. Okay, so that kind of puts the onus on us a bit. Which is great because it's actually, you know, working in this sort of environment. And don't worry for people who had to listen to my talk last year. I'm not going to spend the entire time talking about this like I did last year. It's a fantastic environment to work in because we have a lot of code to play with and a lot of real world examples of where we can really do wonderful things and add a lot of value. You have to keep the engine going, which means that sometimes I sort of rush over here and fix a font bug, and sometimes I kind of rush over there and fix an XML bug, and then, oh, the JVM is crashing. I'll rush over here and do that. I only fix the fonts in XML because Martin refuses to do it. That's right, Martin? Yeah. So in that spirit, I am going to spend my talk clumsily lurching from topic to topic. Which is very much like how I spend most of my time. Last year I talked about static analysis monitoring in GC, and if you are interested in static analysis, originally I thought this was an hour-long talk, and I put in a section on static analysis. It's actually pretty interesting what we've been able to do, I think, but I had to cut it out because I realized it was a 45-minute talk. If you're interested in monitoring GC, I'm happy to talk to you about that at length. I talked about it last year, but I was told it wasn't JVM Language Summit friendly enough. So I have changed the topic this year. This year I'm talking about native code. And I wrote a lot of my talk before I saw the last day and a half, so pardon me if it's a little bit repetitive. I am talking about multi-threading, which everybody loves, right? And I won't be able to get to static analysis because I simply won't have the time, unless you want me to give a lightning talk on that, but you probably don't. So let's talk a little bit about native code, as if we haven't talked about it enough already for the last day and a half, if you're not completely sick of the subject. We've had lots of talks about JNI and JNA and JNR and packed arrays and structured arrays, and I think what I've noticed a bit from the crowd is that there is a little bit of confusion about why you would use native code. There seems to be a bit of a feeling that, well, you know, you need to call getPID, so let's make a little hole and we can call getPID. Or you need to call select and let's make a little hole and you can call select. And other than that, let's stay as far away from native code as humanly possible. That is not what happens at Google. I can't speak for other companies, but that is certainly not what happens at Google. There are two major reasons that we don't do that at Google. One is that, well, performance and predictability can be an issue. I'm being snarky here. Yeah, maybe you need a 2 to the 32 length array. I'm sure I'm going to get an argument from John on that. But the fact of the matter is, if you want to have a chunk of your code where you go down to the bare metal and get that last ounce of performance out, and you're writing in assembly and you want to write a huge chunk of it in assembly, or whatever, even if you want to be guaranteed 100% down to the microsecond that you're not going to have any garbage collection pauses, then performance and predictability can be an issue. And we do operate at the kind of scale where sometimes that stuff does actually come up. You know, if you add enough zeros to that, you know, to anything, then the performance problem does actually appear. The other part of it, which is also interesting, is that We actually have several different languages that we support at Google, and there's a common infrastructure for each of them. You know, if we're writing servers in Go, and we're writing servers in Java, and we're writing servers in Python, and we're writing servers in C++, a lot of the low-level infrastructure-y things are going to have to be exactly the same across all of those. So what do? You have two choices. One of those choices is to write it 4 times, or 5 times, or 6 times, or 7 times, or 8 times. And the other is write it once and have it be available for all of your clients. It becomes very complicated to write it once and have it available for all of your clients if you're writing stuff in Java. You know, I guess if we had a Python that ran on the JVM and a Go that ran on the JVM, and I guess a C++ that ran on the JVM, maybe that wouldn't work so well, never mind. So fundamentally, we have that. And we need the C++. So I wanted to stick this slide up here just to sort of explain why I'm going to spend a lot of this a good chunk of the conversation talking about C++. Even in the audience, I got into a few conversations about why on earth we would use C++. So I wanted to make it a bit clearer. I probably shouldn't have put the word obvious here. This is not the easy stuff. This is the hard stuff. There are the engineering level challenges, and we've talked about the engineering level challenges today, and we've talked about the engineering level challenges yesterday, and they're hard. And we hit them all the time. So I'm moving on to the part of my talk where I talk about the challenges. The data layout is different. Object and lifetime in Java is a very dubious notion. This came up yesterday when we were talking. You want some way of being able to free that memory you mallocked. And Java just doesn't let you do that in a very predictable way unless you actually stick in a call to free, but Java programmers don't like to stick in calls to free. They like the garbage collector to take care of it, things like that. There's no such thing as a pointer in Java. You're always punning with JLongs. JNI is slow. Yeah, well, you know, you guys are going to fix that, right? No problem, great. There are mismatches between the memory models. We had this big memory model conversation earlier today, and, well, mismatches may not be the right word. It is important for a C++ programmer and a Java programmer to understand what to expect when they share memory across multiple threads, or what guarantees they're going to get. I wonder why my dock isn't going away. Whatever. And those are the engineering ones, but there's also a lot of workflow ones. And this is somewhat more soft than some of those other ones. And I want to talk about some of the soft things because they're still challenging to get through. There are different assumptions about your runtime environment. Like a C++ person can just, you know, they feel like they can install a signal handler and it's not a problem. And then you stick that into a blob of JNI and all of a sudden their code starts to fall over and you have to explain to them why that's a problem. What do thread IDs look like? You wouldn't even think that that would be a problem, right? But all of a sudden, you know, your native thread ID is something that's different from your Java thread ID, which is just an integer that gets incremented. How do you handle when you have malloc going on in your process? You know, what happens when you have, you know, what does that mean to a user? And I'll talk about what I mean by that in a couple of slides. You have different best practices. You know, C++ users simply write their programs differently from Java users. You get things like, well, when there's an error, just crash, you know, and somebody can clean up later, right? They don't throw exceptions. And so we will have people calling into JNI from their Java code and wondering why everything crashed. Debugging is painful. I'll talk a little bit more about that, but anybody who has debugged JNI knows that debugging is kind of a painful topic. Monitoring is painful. There is such a mismatch between these communities that sometimes you have to explain, you know, well, there are a lot of very naive Java programmers out there. There are a lot of very naive C++ programmers out there. And sometimes you just have to explain why your RAM increasing has nothing to do with your Java heap, or vice versa, right? Or, you know, Java heap issues have nothing to do with the amount of RAM you're using, right? You know, just explaining to them why memory that you've allocated has nothing to do with, you know, what you're doing in Java is hard. And then there's this sort of disdain that people have in both communities for each other, right? I think that's actually that can be a real challenge when dealing with both of the users. And I see my counterpart from Facebook nodding his head vigorously, having to probably deal with a lot of this. Oh, you're in the I hate C++. Well, right, sure. You know, I'm talking to, yeah. So there you go, exactly. You know, And it doesn't really matter what, I mean, C++ users see Java as frivolous, and why would you use that thing? You can't make any guarantees about it, and it's not predictable. And Java users go, oh my God, that language, it's full of sharp edges, and you're going to shoot yourself in the foot no matter what you do. And so there's this sort of instinctive revulsion that they feel. So even getting them to talk to each other is often very, very hard. My boss actually said to me one time that I was the only person he'd ever met who could speak both languages, which was I'm not sure if it was a compliment or an insult. I'm pretty sure it was an insult, but that's okay. The other thing is the automatic wrapping state of the art, and hopefully you're gonna fix this for us, is Swig. Swig, for those of you who haven't had the pleasure of getting to know Swig, it is basically a C preprocessor that tries its best to look at what you've done in its C preprocessors. It tries its best. It kind of looks at the C++ code. It doesn't actually contain a parser. It contains some heuristics that kind of guess what that would be if it were written in Java instead. And it spits out something that is almost but not entirely exactly unlike what you want it to spit out. So it has this whole markup language where you have to fix it up, and it doesn't really understand C. And fortunately, as the observation has been made several times in this talk, or in this conference, that libclang does exist, and you can write a replacement in front of libclang. And our Python guys are so desperate to get rid of Swig, and they sit next to some of the largest Clang contributors in the world, that they are actually, I was just told last week that they are starting a project to write a replacement for Swig on top of Clang. And so hopefully I will hold the person who told me that to that, and he will have something that is a lot better than Swig. But for those of you who don't know anything about it, consider yourself lucky. So what do we do? Right? We have this huge disconnect. Java users don't want to talk to C++. C++ users don't want to talk to Java. Compile two separate binaries. Have them talk via RPC. If the C++ crashes, it's the C++ people's fault. If the Java crashes, it's the Java people's fault. That's fine. You know, I think you'll probably find that a lot of places are actually just doing something like that. We do it in a lot of places, and yeah, it's fine. The problem is that's not really something you want to do if you are using C++ to get that last ounce of performance. If you have to get that, that byte buffer decoded super, super fast, so you just go into C++ and come back out. That doesn't really work if you talk via RPC, because that kind of kills some of the guarantees. So we try to find ways to mitigate the pain, and I'm not going to talk too much about what we do to mitigate the pain, because I saw Charles hand wave it yesterday, and so I figured I should probably hand wave it too. But we are heavily reliant on launchers. We wrote our own launcher. It turns out that a lot of the pain of deployment and a lot of the pain of JNI go away, and I can talk about this later, if you just compile all your JNI into a static blob and put that in the main executable. A lot of the pain, and play this little trick where elf binaries are the beginning of an executable and jar binaries are the end of an executable, so you can just concatenate them and come out with something that makes a quite nice deployable artifact. It turns out that that actually mitigates a lot of the pain. So we're actually going to force all of our users to do that. Say, if you are interested in JNI, just do that. Fine. I don't want to talk about it more than that because it's interesting. We had actually implemented something very like JEP 178, which allows you to put JNI in your main executable internally, and I could talk about that, but then you guys wrote JEP 178, and so we didn't need to. We had to adjust our tooling to deal with the fact that the mixed mode is painful. What do the debugging tools do? What are the monitoring tools doing? And I'll talk some about that. So the debugging state of the art. And I think I've heard this from people at this conference also. What's the debugging state of the art? Well, you attach a Java debugger, and you attach a C++ debugger, and you keep changing your windows, and you flip it back and forth. Well, I don't like that, and I don't think anybody else likes that either. So we decided to do something about that. And this is sort of like the one thing that I'm probably the most proud of that we're talking about, that I'm going to talk about in this talk, which is that, and you won't be able to see this video. I didn't want to do a live demo, but we made GDB understand both native and Java stack traces. We are desperately trying hard to get this pushed up to GDB. If any of you can hammer on the GDB general maintainers and make them take it, then, oh, whoops, that was supposed to be that's weird. Can I not press play there? So I won't make this a long conversation. Basically, I wanted to show you what I had done, but you can't see this, right? So I'm running a Java program, and it says it turns out this should never be called. This should never be called is the line I am highlighting in that C code. You go back to the main executable, you try to run GDB on Java to figure out what, I wanted to show you exactly how painful it is to try to debug JNI. You run GDB on your Java binary, you execute, you say break at that line where it says this should never be called, and then you run your Java program, which I will get to at some point. And what does it do? Well, give me a backtrace, right? There's a backtrace. That is not a useful backtrace, and you probably can't see that backtrace, so I will bring it up. Fortunately, even though you can't see the video, I did actually keep my bash history up. So this is what it looks like. This is what that backtrace looks like, and hopefully you can see this. This is the backtrace you get if you execute and you die in the middle of JNI, because frankly, GDB doesn't understand Java stacks. So what do we have instead? What do we have instead? Well, I figured if Christian could show his mixed mode stack traces off yesterday, I can show my mixed mode stack traces off today, right? So we do this magic thing where I assume that we load a JIT reader in GDB, and actually I probably could just have scrolled through the rest of it. We do a little magic incantation because there's a bug, and then we say, okay, now give me the backtrace. And now when you get the backtrace, hey, there you go. You can't see that either, so that's all right. I'll scroll down a bit. What do we get? We get a backtrace. We actually get the fact that this was called in this Java method with these arguments and on this line of this piece of code. And this has actually kind of changed the way we do JNI debugging, so we're really trying hard to push it. So that's why I've spent 2 minutes talking about it. Forgive my little indulgence. Yeah, go ahead.
Are those patches out anywhere?
Yeah, we have been, so there is a little patch for GDB, and there is a little patch for the serviceability agent, and we have sent this patch to the GDB list multiple times. We sent it at the beginning of the year. About 3 months in, they said, we won't accept it like this, please do it like that. So we did it like that, and here we are 4 months later. So we really would like to get that stuff sorted out. But yeah, if you go on the GDB mailing list, and I can forward you the information later. You'd have to search for the guy's name who did it, and so on and so forth. So, all right, so that is a contribution that we are hoping to make to better debugging. It doesn't really just extend to debugging, though. It extends everywhere. There are pretty much no tools that put out good mixed mode stack traces. So we have a bunch of tools that do this kind of performance, that do performance analysis. We have CPU profilers, we have heap analysis profilers that sort of say, sample allocations and tell me the stack trace of where those sampling happened. And you can get a Java stack trace out, and you can get a C++ stack trace out, and you have to kind of mush them together to figure out what's going on. So we've had to do a lot of work to do that. And so I guess one thing that I'm here to ask, if I am here to ask anything, is make it possible to do this stuff. There's a whole story behind making good stack traces that extends to languages that run on the JVM and hiding the thousands and thousands, and it applies to Java too, but you saw it apply to JRuby, you see it applied to the other languages, that deals with hiding these thousands and thousands of frames of goop. But there's also this, what if you're dealing with a language that isn't even in the JVM? And it would be nice to get that sort of thing in. The other problem is that our dynamic analysis tools for C++ have to work with JNI and have to work with our Valgrind-like tool that detects memory errors, that he's after free, so on and so forth. It's a very good tool, but it expects to be able to control the entire process. So we have to find ways of saying, okay, Java, you use this malloc, right? And the ways that we do that now with hacks like LD preload, if you're familiar with that, they're actually quite painful to use. And it would be nice if they were, a little easier. Here's where I get a little bit more interesting for people who are interested in more complicated things or differently complicated things. We are also working on a data race detector. We don't actually have it working for Java yet, but we do have it working for C++. What happens when that C++ is running in a Java process? Well, you need some way for it to communicate. And very specifically, if you have any of this, you have the situation, if you have any mixed mode applications, you almost certainly have a situation where a C++ object is allocated in a constructor and is freed in a finalizer. And that's where the happens before relationship is. There's a happens before relationship between a constructor and the finalizer. And that's not understood by the C++ tools at the C++ level. So we actually need to cut a little hole into the C++ tools and tell it when the happens before relationships happen. And we're working on that integration. This is sort of our first task because it's the thing that is hurting the C++ users the most who want to use these tools. But it does involve some JVM hacking to expose the notion of a happens before relationship to external tooling, to a C++ or something like that. You have a little callback that says, I have a happens before relationship. It starts here and it ends here, and this is what goes in the middle. We're starting down the path. We're starting down this path now towards a complete data race checker, and maybe next year or something I'll be presenting on our complete data race checker. But it depends on how fast we can get done with some of the other stuff. So I've been yammering on about native code for the last 20 minutes and probably bored half of you to tears. And so I thought I'd talk about something that's deeply experimental and also has to do with native code, but is more JVM-ish, right? Is more what does this actually have to do with fancy new things that you're doing with Java? And so what I came down with is my old pal threading, which I absolutely adore. What we're doing with it right now is very experimental. In fact, I've sort of been treating it as a 20% project, and at some point somebody gave me a second team to manage, and the 20% project became like a 2% project. But we've made some pretty interesting progress on it already, so I want to talk about what we've done with that. And it is related to other conversations like the JRuby conversation, because I'm going to be talking about fibers. And that's of interest to people, I think. So let's take a step back. I gave a bit of an introduction to Google and how we use Java. Let's talk a little bit about how our programs are structured at Google, because I think that's an important step to understanding what we're doing with threads. Basically, you can think of a Google server or any server in some sense as being three parts. You've got a client, and maybe that runs on a phone, or maybe that runs in a web browser or something like that. And you've got a back end, and that's, a database, basically. And you've got something in the middle, which we call a front end, but, frankly, depending on what kind of development you're interested in, you're going to be calling something else a front end and something else a back end, right? Because to most people, all of this stuff the thing that I'm calling a front end is actually a back end. You've got a front end, it's written in Java, and it's got some logic for dealing with the thing that you just requested from the server and sending it back off to the client. So that's a large number of programs, and a large number of different kinds of programs actually decompose to something that looks kind of like this, right? Even if your client is the person sitting at the keyboard, and your front end is some program that you're running, and your back end is disk you're reading off of. So how do we write those sorts of programs? Well, they're all kind of multi-threaded. They're dealing with maybe thousands of concurrent requests, or tens of thousands of concurrent requests, or hundreds of thousands of concurrent requests, or whatever it is. And the obvious way to write the program like this is every time a request comes in, you spawn another thread, and that thread goes off and deals with the request. And if the thread has to do more I/O, for example, if it has to talk to a backend, it just blocks. It stops. It says, okay, well, wake me when the request comes back. I'm falling asleep here. And we call that synchronous, and it's very easy to understand code that looks like this. It's very straightforward. It's very straight line. You get, pardon me if I'm boring a bunch of people who already know this, but it's very straightforward. It's very straight line. You say, please issue an RPC and give me back a result, and I'll block while that happens. And then you say, okay, well, maybe there's another RPC that you have to issue. Okay, please issue an RPC and send me back that result, and I'll block while that happens. And then finally, I'll have a result, and I'll return it. And that's called synchronous because it's synchronous with the back end. It's waiting for the back end to finish. And the great thing about this is it's totally straight line code. It's ultra simple. There's good locality. You can look at the code and understand it. You can and resources that are owned by that thread continue to be owned by that thread, which is actually kind of neat. The problem is when you fork 100,000 threads or 10,000 threads or however many threads you have as you have concurrent requests. That can be a problem in a server. It's really hard to have that many threads going on at once, and the results are manifold. There can be a lot of unpredictable contention on resources. Everything competing with the OS scheduler to get scheduled. Oh, schedule me, oh, schedule me, oh, schedule me. There's a lot of context switching. Turns out, OS context switching overhead, when you get that kind of number, when you get that kind of number of threads, it gets pretty high. And it turns out that thread scheduling itself ends up being really, really expensive when you get that high. It starts to dominate the costs of the context switch. And there's a lot of thread stack usage, which translates to a lot of RAM usage. By default in the hotspot 64-bit, each thread stack is a megabyte. Well, and then you have 1,000 of those, or then you have 10,000 of those, and then, we'll start to talk about real numbers. It's also harder to parallelize individual requests because, it's all single-threaded. So if there's something that in the individual request you want to do in parallel, you have to kind of handcraft some parallelism. So what do people do instead? Because they can't write this kind of code in servers that scale at all. What do they do instead? They write asynchronous code. And what does asynchronous code look like? Well, basically, every time a request comes in, you dispatch to a thread pool, and that thread pool says, I'm supposed to do this one thing for this request, and here's a callback for when, and then you go issue that I/O, and when that I/O gets issued, come back, and here's a callback that you execute when that I/O comes. So you end up with kind of weird-looking code here. I mean, the RPC gets a request and a response, and it gets a request. And I've actually lambdafied this. We're not actually using Java 8 yet at all, so you can imagine the same thing, but with lots of inner classes and extraneous things everywhere. And so Java 8 and lambdas make it a little bit smaller, but it's still the same problem, which is that this code is harder to read, right? Here you say, here's an RPC. I'm going to send a request that involves the request ID, and here's a lambda that gets executed when you get the result of that request. And then you do the same thing. And it's like, okay, well, I'm going to issue another RPC, and here's a lambda that gets executed when you finish that request, and so on and so forth. So you end up with much harder to read code. And I mean, you can imagine how this is harder to read in a small way, but it gets harder to read in a much, much bigger way when these things get bigger. The pro is that this scales really, really well, right? Because you can have one thread per core, and they're all doing these tiny little chunks of work. And you have a thread pool, and maybe you've only got as many threads as you have cores, although that's unlikely. And so you don't have to worry about the issues of having too many threads. You have exactly as many threads as you need. The cons of this are that all of a sudden, that wonderful feature that you had earlier where you could look at the code and understand it, that's gone, right? In order to understand a request, you can't look at the code. What you need to do is you need to create a state machine that involves transitions between all of these callbacks. And you need to wire that up somehow. Now, there are some people who actually really love having that state machine, the people who have really, really, really bought into this. They say, well, if you've got the state machine, then you can monitor the state machine very carefully, and you can put in all sorts of interesting monitoring and things like that. And that's great and all, but it confuses the heck out of most programmers. Debuggers are pretty awful Because now all of a sudden you can't tell how you got anywhere, right? You're not stepping through code. This callback came in, and well, where did that callback come from? And the stack trace is just, there's the callback. Well, okay, fine, but that doesn't tell you anything. Non-multi-threaded requests are now multi-threaded. Previous code was straight line. This code is now, all that stuff could be executing in multi-threads, in multiple threads. So if you have data that pertains to one request, you now have to do all of the multi-threaded logic. And it's lousy locality because resources are now smeared across threads. So what do you do? Well, everybody knows what you do, right? I guess I just spent, 6 minutes introducing that topic, but you already know all about it. You want something that has the simplicity of synchronous threading and the performance of asynchronous threading, and surely my language can do something deep and complicated to take care of this. Yeah, sure, lots of programming languages have solved this. You end up writing the code synchronously, more or less, and you implement continuations or coroutines or call CC or yield return, and that gives you like a little chunk of work instead of this great big thread stack. And then you sort of farm them out to a bunch of threads under the covers, and you call that a go routine, or you call that a fiber, or you call that whatever you want to call it. And then you add some form of scheduling mechanism to that. You say, please, when you pull a request off of this. I've got a queue of things to do. Pull a request off of this queue and go run it, and hopefully you're done. You've solved that problem. So it's simple, right? That's why Java has coroutines and fibers today. Oh wait, no, it doesn't. So this ends up being exactly, great. This ends up being wonderful. We do this in Go, which is if I've mentioned Go a few times, maybe you guys don't know Go. You know Go. It's a language from Google. And it doesn't have 1 megabyte stacks times 10,000 pending threads. It has a little tiny continuation for everything. And you don't spend all of your time trying to pass through the OS scheduler. And if you're very, very careful, you can actually have really nice locality. So for example, if a request is coming down off the wire, excuse me, you read from the socket, you say, oh, well, this is Bob over there wants to deal with this. Let's schedule Bob immediately. And so on this thread. And so that can be really nice in terms of not bouncing back and forth between multiple threads. I should have put the hard to explain part of this talk at the beginning. I'm running out of energy. So approaches, well, there are 80 bazillion prior Java JVM language summit talks on continuations. The approach is usually very simple. When you block, instead of blocking, you save some chunk of state, and then you switch to something, you go execute something else. And you need some user code that tells you what to switch to, and you need to manage your threads somehow, and Bob's your uncle. And there is going to be a talk by Ron Pressler tomorrow that describes how you can do that with bytecode rewriting, and he's got some much more impressive demos than I have, because I don't really have time for demos. But now you find out why I actually spent the first 20 minutes of this talk talking about JNI, which is that approach doesn't work for non-Java threads. If you find yourself in native code, all of a sudden, there's not much you can do there. So how do we solve this? Gives me a headache just thinking about it. Well, you could build some sort of support into the JVM. And it turns out we had already done that. About 5 years ago, my colleague Hiroshi Yamauchi built some experimental continuation support into the JVM. And he gave a talk on it at the JVM Languages Summit with the other 80 bazillion continuation talks that have no doubt been given. And it's a pretty simple API, and could we leverage that? Well, probably, but we haven't gotten around to it. The continuation support in there is actually really simple. Enter means start the bit you might save, because the continuation involves saving some chunk of the stack. Save means save everything you've done since you started, and resume simply says pick up where you left off. And then you go and instrument your blocking calls. And we can talk about that, offline if you want, in more detail. So what do you get? Well, the debugging is definitely better. All of a sudden, all those Java stacks that didn't make sense before make sense, because you've got a nice clean stack. The memory consumption problem goes away, and the users don't have to think in an asynchronous way. If you have 10,000 threads, I ran something over the weekend. It may have been completely bogus. I did a little experiment where I started 10,000 threads, went to a certain stack size. I got about 1.2 gigabytes of RAM usage, which actually I didn't think was a lot, which I was surprised at. I think I probably just did the experiment wrong. You can also have, but you can have 10,000 of these continuations going in your VM, and that's 30 megabytes of RAM. And that's a substantial improvement. And the performance was comparable with async. And I think it was a couple of % off, but I think largely that's a result of the experimental nature of the patch. But the con of that was that the continuation was something that still didn't work for Java code, non-Java code, excuse me. It could take a little chunk of the stack, reify it into something like tiny, and save it somewhere, but it couldn't take something it doesn't understand, which is that C++ stack, and reify it and turn it into something interesting. So what do we do instead? Well, I think we have to go deeper in this case. And fortunately, we have some very smart kernel hackers at Google. If you do this stuff in the kernel, it turns out that all you have to do is swap out a bunch of registers. And you can do the register swapping on the userland side, but you have a kernel level. If you really want to get into the JNI, you have a kernel level notion of what a thread is. So if you really want all of that per thread state saved, you kind of want to go into the kernel to do it. So all you need to do is swap out a bunch of registers. And if you do what I said earlier and you say, oh, well, I've instrumented my queue and I know exactly what's coming in off the queue. It's this thread. I want to schedule that thread next. You can just tell the kernel scheduler, oh, go ahead and schedule this thread next. And it will switch out the registers, and it will schedule that thread next, and it's really, really, really fast. And you get your entire JNI context. So it's a very, very simple API for this. I mean, you can say, there are only 3 operations, basically, and you can build an entire set of building blocks, of concurrency building blocks around them. You can say, please give up control. I'm done processing. Do something else. Give up control. You can say, at some point later, resume that guy's control. And the third thing you can say is just, from me, go and switch to this other thread. And that is the fast user switching operation that encapsulates the cool thing about this work. And this works for JNI, which is great. All it means is you've got this stack, it's got the JNI on it, and you're executing that stack now. That's it. You just switch right over. And the context switches are really, really fast. The context switches for the handoffs are now 150 to 200 nanoseconds. I was looking at Ron's talk. He's probably going to smirk because I think he had pretty similar, he did it all in bytecode, and I think he had pretty similar timing. So maybe it's not that lightning fast, but 150 to 200 nanoseconds is pretty good for a context switch. The kernel call itself turns out it's really cheap. The hardware vendors have been working for years making the kernel calls really, really cheap. You don't need to do the scheduling. The scheduling turns out to be the expensive part of a context switch, having the OS decide what thread to schedule next. And you also save this interesting phenomenon you get where if I want to wake up that guy over there, if I'm a thread and I want to wake up that thread over there, I say, hey, wake up. It wakes up. It probably wakes up on another core. I go to sleep on this core. And now all of a sudden, the processing that I wanted that thread to do is being done on this other core. And it's very likely that that thread wanted to work on the same stuff that I'm working on. So you get a cache. Your cache gets flushed, and it goes over the wire. It comes back on this thread. And you get this really, really expensive two-step process here that just doesn't happen when you say, please give that other guy my thread. So that's kind of neat. Debugging is still great. A thread stack is a thread stack is a thread stack. That's it. Existing code just works. In fact, you take out all of this switch to stuff, and it just gets a little slower. It's not that big a deal. The locality is nicer. As I said, you can switch directly to the code that you want. You can switch directly to the thread context that you want this code executing in. You don't need a nanny scheduler. Those of you who have seen scheduler activations or Windows user mode scheduling, you might be familiar with those. It sounds a lot like that. That's the distinction here. You can just say, please switch to that thread. With Windows or with scheduler activations, you have a little blob that the OS executes in user space to make the decision. But there is a problem here, and that problem is thread stacks. And it turns out that, you know, if I go back to before and I mentioned, you know, you have 10,000 thread stacks and it's going to start costing you some memory, that problem doesn't go away because you have 10,000 thread stacks. And this actually turns out to be a problem on all of our code, regardless of whether it's doing this. So we had actually come up with a completely separate solution for this problem to try to shrink the amount of RAM usage for a given stack. And it's a really, really simple, dead simple solution, which is if you're not using the end of your stack, just everything off the end of your stack, tell the operating system you don't need it anymore. The operating system will reclaim that memory, and your RAM usage will go down. And if you guys don't know why I'm worried about RAM usage, and you think I should just use swap or something, then you go tell Google Search that they should swap in the middle of your search query and see what happens. So that's what we do. I mean, that's what we do here. We can make these thread stacks substantially smaller by just saying, get rid of all of the memory you're not using. Is it smaller enough? Well, no. It's not really smaller enough, which is where I get to the more expensive. It's smaller enough for most usages, but it's not nearly as nice as continuations are. Here's that same benchmark I mentioned before where I started up 10,000 threads and we did lots of stuff there. And you'll notice that the naive threading implementation that doesn't do anything, just starts up 10,000 threads, uses a bunch of memory, and lets them sit there, that's using 1.2 gigabytes of RAM. The implementation where I return the unused RAM to memory after I'm done with it, and I just had the stacks go up and down randomly, you know, that saved a lot of RAM. And it saves a lot of RAM on our servers, too. Without using this stuff at all, it just saves a lot of RAM. It saves 900 megabytes in this benchmark stress test that I cooked up, which is great. 300 megabytes, that's much smaller than 1.2 gigabytes, but 30 megabytes is a lot smaller than 1.2 gigabytes. It'd be nice to get that back. But we have this tension between saving the JNI state and being able to create a tiny little continuation that is currently still work in progress. So as I said, this is experimental work. And pretty much I've reached today. So I don't actually have a good ending to this story. This is where I am today. This is what is today's date, the 29th? Oh, yeah, it's the 29th. I think it's the 29th. I'm going to say it's the 29th. This is not a solution for everyone, obviously, unless the Linux kernel picks up the Switch 2 patch. And even then, it's only a solution for people using Linux. So I would actually probably advocate for something similar to this approach, but not identical, in the JVM. And I'd have to work through the details of that. And like I said, this is a slide I cooked up at 12:30 in the morning last night when I decided I didn't actually have a finish to this talk. You could probably have a dedicated green thread and have it actually do the swapping out of registers on demand. You could improve the memory situation by having what's called a cactus stack, which is that you have a regular stack, but with a continuation, you kind of share a stack with, you share the bottom of your stack with other things in the continuation. So you can imagine a cactus stack as a stack that, you know, it goes up this way if you have one continuation, it kind of goes up this way. If it has another continuation, it kind of goes up this way. If you have another continuation, look it up on Wikipedia, I've run out of time. Language support would also be nice for this stuff, but I think in some sense, that's well, I don't know if it's not the easy part, but it would be nice, and it's something that I think, you know, Java 12, Java 13, whatever it is, we can talk about it. And now I'm stopping abruptly, and I actually ran out of time, and I'm stopping abruptly at the same time. There are no great morals to be found here, I'm sorry. But do you have questions, to the extent that I have the time to answer them? Charles?
The other code-review project I know about is Lucas's work.
Kill him. Mm-hmm. Yeah, for coroutines, you absolutely do that. And that's, you know, when you have coroutines, which we don't with the threading work, I think it is certainly possible. So I should repeat the question for the mic. Charles points out that people building on top of LLVM doing continuations actually have a solution where you only lazily copy the bits of the stack that you need. And that saves... Oh, I'm sorry, MLVM. Yeah, that makes more sense than LLVM, yeah. Yeah, that's good for continuations, and it probably still works. Hiroshi's solution probably Hiroshi's solution does, excuse me, it does copy them eagerly. It could be made to copy them lazily. But I haven't really talked about the overhead of copying the chunk of the stack that you need here. And yeah, that would be a way of making the reification process cheaper.
You earlier showed the native Java stack frame call walking. And on that end, just a quick thing is, so you have a glue library that between debugger and the JVM.
So are you asking how we do the mixed mode stack walking?
I'm actually getting to point that, is it specific, Java version specific, or?
The GDB stuff?
Yes.
You do need a patch to the JDK. It is a patch to something called the serviceability agent, which you may be familiar with. It is not that big a deal patch. So you would have to have a JDK that supports it. I expect that it would be a lot easier to get this community to agree to support that kind of stuff than it's been to get GDB. So we've been kind of pressing on GDB first. But yeah, you would need a special version of Java.
Yes.
Yeah.
We actually did a similar patch.
Oh, you did a similar patch?
Well, not I, but
I mean, your team.
at Twitter, yes.
At Twitter, yeah. Yeah, I'm not claiming that that was amazing research work, but it has made our JNI hacking a lot easier. And so that's why I wanted to show it, just because, especially since Christian mentioned yesterday, like, oh, we've got ahead of time compilation, you can actually get a GCC, you can get a GDB stack. It's not limited to places where you can get ahead of time compilation, you just need the right appropriate support in.
Follow up to that question. This is wishful thinking, but would it help you to have support in the JVM for introspecting its own stacks? Or that's, there's no way you can do
well,
it?
for the JVM stack or for the Java stack. So for the stacks that are in like the runtime, so John asked if it would help if we had support in the JVM for introspecting its own stacks. And if you're talking about something like a GC thread,
Java
you can
application
just get
threads
that with
too.
GDB, right? What?
Application threads.
Oh, application threads. Well, yes, and that's kind of what we patched in for a serviceability agent. You say, okay, well, you know, here's this thread. You know the current state of the application. Can you just tell me what? And here's this program counter, and can you just tell me what it is, right? So,
Not via SA, but through a call to a Java utility. Is there any chance?
You mean like?
Doing an
oh, but
upcalling
then
to
you're
VM
calling Java from
to have it
GDB.
spill its guts. Yeah.
Yeah. Well, I mean, GDB actually has it has an interface for this that's written in Python. So it doesn't really, in some sense, it doesn't really matter what the glue layer is. You just have to make something that sort of meets that Python. I'm running way too over time, aren't I? Yeah. Okay. Yeah. So we can talk about that later. But I would probably use such a patch for whatever it's worth, but for other things. Getting a mixed mode stack trace out would be a lovely thing to be able to do. I mean, we have it and we hacked it in, but.
We have some work ongoing for a better stack walker, but it's from inside Java.
Oh, yeah. Yeah, well, so I read, I don't remember if it was Mandy Chung who sent out a JEP on this. Yeah, well, just getting that out faster, we've had to do a bunch of stuff to get out stack traces quickly. That is a substantial investment, and we've done a lot of work around minimizing the cost of getting out stack traces. Happy to talk about that offline if you like. Did you say one last question? I don't know if there is one last question.
That was, you heard it there. That was the last question.
Oh, that was the last question.
Oh, no,
okay.
okay, one more.
Okay.
So maybe you mentioned it already, but I'm trying to understand the scale of the problem that you were trying to solve when you were talking about thread
I
stacks
was
and
vague
trying
about
to,
the scale of the problem that I was trying to solve. So you
when
think
you're
like
talking
900
about
megabytes is
saving
not
300 megabytes,
No, talking
why
about
do we
saving. I was
care?
talking about saving 1.5 gigabytes. Any number I say is not an officially sanctioned number by my employer, obviously. Whatever number I say, Google has a lot of machines, and Google has a lot of programs running on that large number of machines. And so you can imagine if you start adding zeros to things, then numbers get very large very quickly.
So in terms of follow-up question, there will be, so if I understood you correctly, you were trying to unmap whatever stack was unused, and that's how you drop the RSS down. So
Yep.
is that stack that's going to be reused again if the application makes calls?
If the application needs it again, then it will just grab it again, yes. But it turns out that when your application is, you can sort of, it becomes a steady state thing where you're always removing stack. And so you, on average, use less than you otherwise would. And we've actually seen some very nice savings from simply doing this in our regular applications. And I should let Vlad do his lightning talk.
Thank you.
So thank you.